Should be okay. So, hello. Today we'll talk about linear models for classification. First of all, we'll start with a bit of remembering of the of some concepts that I'm sure that all of you know about classification, and then we'll start building from there with new information that I have to transmit you. So, a little remember. At classification, the purpose is to take an input vector x and assign it to one of the k discrete classes, ck. Most of the time, the classes are disjoint, but there are also tasks where points may be assigned to multiple classes. However, today we'll be talking about disjoint classes, so every point should be assigned to one and only one class. The space, the problem space is divided in decision regions that are limited by decision boundaries or decision surfaces. And if we would like to build a linear model for classification, it means that this decision surface is a linear function of the input vector x. So in other words, y of x may be written as w transpose multiplied by x plus w0, that is the bias. If we have a data set that may be separated correctly, exactly by a linear decision surface, that data set is called linearly separable. However, in real life, such data sets are really unicorn. You may not find such data sets in reality because there are a lot of errors that might affect the data set, and therefore there might be points that are misclassified or features that are not correctly captured in the data set. By the way, if there is any question that you would like to ask, or if there is something that is not clear, please stop me, and I will try to explain again and again those concepts in order for you to understand what I'm trying to say. Now, the target values for classification. If we have a binary classification, so only two classes, then we would like to have a binary representation. I mean, 0 or 1. And most of the time, we typically use a single real valued output that has target values of 1 for the positive class and 0 or sometimes -1 for the other classes, for the other class. Do you happen to know when we use -1? Because it's for most of the classification tasks, we would use this value of 0 for the negative class. Do you happen to know when do we have the value of -1? So when do we have this for the negative class? Anyone? Have you ever met the value -1 for the negative class? Okay.
Is it used for those kind of tasks where you intentionally have a bias towards identifying positive examples, and -1 doesn't necessarily signify the presence of the second class, but rather the absence of the first one?
No, in fact, it's this -1 is used in a class that is much more popular. You know, perceptron.
Yeah.
In perceptron, you have +1 for the positive class and -1 for the
Okay.
negative
Okay.
class.
Yeah.
So it's quite I don't know, popular for neural networks. to have this value of -1. Okay, for probabilistic models, the target value t can be interpreted as the probability of the positive class, and also the output of the model is said to be the probability of the model to give the positive class. So if we have a probabilistic model, then the output of the model might be some value in the interval, real value in the interval 0, 1. So maybe 0.25 or 0.83 or any value in this interval. And this should be considered as the probability to have a positive sample there. Of course, if the value is greater than 0.5, then we'll interpret this probability as being for a sample from the positive class. If it's below 0.5, then that sample should be classified as being part in negative class. But we also have these probabilities that will tell us how confident we are that the class that we decided or we established is the true class. However, this is happening when we only have two classes. If we have more than two classes, so if we have n classes, most of the time we use for the target values a representation 1 out of k is called. That is a vector made of n different values, target values, consisting of zeros and 1 unit. All the vector is 0 except for the class that corresponds to that sample, and that position will have the value of 1. Again, for probabilistic models, we will interpret tk as being the probability that the class of the sample is ck. And we have an example here to be easier to understand. If we have k equal to 5, so we have 5 classes, and the target belongs to the class 2, it means that we have 0 for all the other classes, for class 1, 3, 4, and 5. And we have this value of 1 for class that we are interested in, C2 in our case. Okay, everything clear? Now, as I told you in the previous lecture, there are 3 different possibilities to use in classification. Either use a discriminant function, which directly maps the input data in output data. So in our case, in the class of the input data. So it converts the input vector x into one or more real values, so that a simple operation like thresholding may be applied in order to obtain the class. But we don't have probabilities. Is the easiest way of doing classification, but however is prone to multiple problems that I presented in the previous lecture. Then we might have discriminative models that infer conditional class probabilities directly. So is the probability of class ck given the point x? In other words, what is the probability of x to be part in each of these classes? So what we have to do is to compute this conditional probability for each class, and afterwards to make the decision that minimizes some loss function. This is a bit more complex method than using discriminant function. However, it's not as complex as a generative model, which models, in fact, the class conditional density, so probability of x given class. And then we model the probability P of ck, so probability of class. This is easy to evaluate because from training data, we simply have to compute how many points are in each class, and based on those counts, we divide the number of points from one class to the summation of all the points, or to the total number of points. And once we have the probability of x given ck, which depends on the problem, how we compute, and the probability of the class, then all we have to do is to use Bayes' theorem in order to detect what we are interested in, namely probability of the class given the point x. So we simply use Bayes' theorem. P of x, actually we're not interested in this, because what we will have to do afterwards is to compare some of these probabilities, and based on these probabilities we simply have to use or assign the point x to the class having the highest probability. And since p of x is not changing its value during this phase, we simply need to compute the product of these two elements. So once we know the probability of x given the class and the probability of the class, we simply take the product and then assign the point x to the class that will provide the highest value for this product. Now, in this lecture, we will not work gradually. So first of all, we will start with some discriminant functions, but then instead of going to discriminant models, we'll step forward and go to generative models, and then we'll come back to discriminative models. And we'll see why we're not respecting the right order, let's say, to evaluate them or to talk about them in order or their difficulty in a few slides. So now we will get back to this slide. In order to predict the classes, if we have a linear regression, because you did that in the last lecture that was presented by Traian, all we have to do is to evaluate y of x as being w transpose multiplied by x plus the bias w0, and then the value that is obtained, this value of y, is a real value. So this is what we had to do. However, for classification, we need to predict discrete class labels. So basically what we have to do is to transform the real value, the value of y, using a nonlinear activation function, f, so that to get only discrete class labels. And therefore, this new model that is obtained is called the generalized linear model, and is nothing more than sorry, I don't know what's happening. It's nothing more than what you did for regression, but afterwards taken through a nonlinear function f. And as a fact, the inverse of the activation function is called link function. Any questions so far? Okay, then we'll continue. So, as I told you, we'll start with discriminant function, and first of all, we'll talk about two classes, because this is the easiest classification task. So first, we'll talk about linear discriminants. Linear discriminants are discriminant functions for which the decision surfaces are hyperplanes. So we have y of x equal to w transpose x plus w0, and w0 is called the bias. W transposed is the weight vector, and also minus w0 is called the threshold. Do you know why? You know, we in most models we have this condition: if y of x is greater or equal to 0, then x is assigned to C1. If y of x is smaller than 0, it means that x will be placed in class C2. However, if y of x is defined like this, if we compare W transpose x, so we have this is greater or equal to 0. This is a real value, so it means that what we need to do, in fact, is to compare this value with minus W0. So actually, that means that we have to compute this product and to compare it with a threshold, right? To see if it's lower or greater than this value. And this is why minus W0 is called the threshold. The decision surface. So these are the linear discriminants. The decision surface, it's d minus one dimension hyperplane that is found in the d-dimensional input space, defined by the equation y of x equal to 0. So if we have only two classes, then we will have to define the hyperplane that will separate these two classes, and that means that y of x equals to 0. And now, how can we detect this decision surface? Because once we detect the decision surface, we may be able to evaluate any kind of point from the space. And the problem is, how can we find it? What do we need to know? Well, there are only two things that we are interested in. Its orientation, in order to know how to place it in the space, and offset from origin to see how far or how close from origin this hyperplane is set. And this is what we will try to find out. How can we identify the orientation and the offset of the decision surface? And now let's suppose that we have 2 points, xa and xb, that are especially on the surface. Okay, so it means that if they are on the surface, y of xa equals to y of xb equals to 0. So that translates to the fact that W transpose multiplied by xa plus W0 equals to W transposed multiplied by xb plus W0. And now, of course, and this equals to 0. I will try to subtract the first part, the second part from the first part. And that means that W0 will disappear. And we will have W transposed multiplied by XA minus XB equals to 0. So this is the formula that we are interested in. What means this formula? What's its purpose? Why we set it here? Well, it means that if we know some points from the decision surface, then the weights vector W will be orthogonal on any such vector that lies within the decision surface. And this is extremely important because, you know, if the points from the decision surface are all orthogonal on W transposed, so on the vector of the weights on this W, it means that this W in actually determines the orientation of the surface, because once we construct the vector W, so the green vector from this figure, it means that all we have to do is to draw the perpendicular on this W, and that will be the decision surface. Moreover, I told you that we are interested in two things: orientation, and as you can see, orientation is orthogonal on W, and offset. Now, to find out what is the offset, we also use the formula from above, W transpose. So let's see. W, I don't know. W transposed multiplied by XA plus W0 equals to 0. So we take a point from the decision surface. And it means that y of xa equals to 0 because this is the point is on the decision surface. And it means that W transpose multiplied by xa plus W0 equals to 0. If we take W0 on the other side, we obtain this formula. And then what we have to, from here to here, all we had to do is divide both sides, left and right, by the norm of W. Why we did that? Because what's happening now? If we consider, let's take a look on the figure, okay? And in this figure, if we draw the line from the origin to this point, x perpendicular, then to evaluate a new point x, all we have to do is to say, okay, the value of x equals to the vector that I draw, so from origin to this perpendicular, plus the cost of the perpendicular drawn from x to the decision surface. And now, if we consider this equation comes from physics, okay? So if we consider this equation, so the vector x equation that is found in here, the vector x equals to the vector to x perpendicular plus this distance from x to x perpendicular, distance that is written as r, a number that we don't know yet, multiplied by w divided by the norm of w. And once we have this equation, if we multiply this with the W transposed, what we'll get? We'll get W transposed multiplied by X equal to W transposed multiplied by X perpendicular plus R multiplied by W transposed multiplied by W over the norm of W. Now, we'll add in both sides so that in the left hand side we'll have y of x. Do you agree with that? So add w0 to this term, w transposed multiplied by x, we will get y of x. If we add on the other side w0, we'll have w transposed x perpendicular plus w0 plus r multiplied by, can you tell me what is W transposed multiplied by W?
Squared norm.
Squared norm. Okay, perfect. So this is the norm to the square. Now, this term is equal to what?
Y of x perpendicular.
And what should be that value? Is true. So this is y
0
of x perpendicular and equals to 0 because x perpendicular is on the decision surface. So what we get after this, I'll write on top here. So we get y of x equals to r multiplied by w, by the norm of w. Okay, and from here, in order to obtain r, we divide by w, and therefore we get to this formula. Okay, so r equals to y of x divided by the norm of w. So basically, what this is saying, that in order to evaluate the value of x, we have to compute y of x and divide it by the norm, and then we're set. Now, in terms of the position, so we got the orientation of the decision surface right here. So we saw that it's perpendicular on the vector of weights on W, and from here we know the positioning. So W0 will tell me what is the location of the decision surface, because from this computation, we saw that it should have been an A here. Okay. We saw that in order to find this point XA on the surface, we get to this equation that divided by W0 tells me what is the distance from the origin to the decision surface. And that distance is minus W0 divided by the norm of W. Make sense? So if we have W transposed, we know the orientation of the decision surface. And if we have W0, then we have its positioning, because it's the value minus W0 over the norm of W. And now, if we have these two information, these two pieces of information, it means that we know everything about the decision boundary. And therefore, to evaluate a new point X, I showed you that all we have to do is to take the perpendicular from X to the decision boundary and to evaluate this value. If it's positive, then it will be in class C1. If it's negative, then it will be in class C2. Okay? Make sense? And I showed you that the value of R is simply the value of y of x divided by the norm of W. Okay. Now, if we have more than two classes, we have multiple options. One possibility is to use n two-way discriminants that will tell me, look, this point belongs to class 1 or doesn't belong to class 1. This is one classifier. And we'll have to build n such classifiers and such discriminant functions, each of them telling us that one specific point is or isn't in that class. So basically, each function that discriminates one class from the rest. And this is why this possibility, this option, is called one versus the rest classifier. That is one option. Another option is to have n multiplied by n minus 1 divided by 2 two-way discriminant functions. So these options tells us, compares the point that we need to evaluate only between two particular classes. So it's saying, is it in class 1 or is it in class 2? Is it in class 1 or is it in class 3, and so on. And this is why, because we have to compute all the pairs of classes, we will have n multiplied by n minus 1 over 2 two-way discriminant functions. So each function discriminates between two particular classes, and this is why the classifier is called one versus one classifier. However, none of these two options is optimal, because both of them have issues. And here we show the issues. In the left figure, we have the issue when we have one versus the rest. So let's suppose that we have this situation from here, and we have two classifiers, one for C1 and one for C2. So it basically tells us, for example, what's above this line, it belongs to class C1, and what's below it belongs to other class, not C1. Also, what's in the right hand side of this line belongs to C2. What's in the left doesn't belong to C2. And now the problem is the green area belongs to class C1 or to class C2, because according to the classifiers, it should be in class C1, but in the same time it should also be in class C2. So we don't know exactly what is the class of the green area from here. Okay, we don't know what's happening here. Now, this is with the problem with the classifier one versus all, one versus the rest. Now, if we have one versus one classifiers, we have the following problem. So let's suppose we have the picture from the right, and the green area, according to the first classifier, doesn't belong to C1, but it should be in class C2. According to the second classifier, it doesn't belong to C2, but should be placed in C3. And according to the third classifier, it doesn't belong to C3, but should belong to C1. So all these classifiers are contradicting each other. And again, we don't know what to do with this point. So what do you think? What other options do we have? How should we decide what is the value of the green area in both situations? Because we would like to have a solution that works no matter what. Any ideas? Well, the solution for that is to use n-discriminant functions, yi, yj, yk, and so on, one for each class, to evaluate the value yk of x corresponding to each class. So what would be the value or the probability of the point to belong to class k? And for that, we will have a weight of a vector of weights for each class, and also a bias for each class. And then after we compute the value yk of x for all case, for all classes, then all we have to do is to assign the value, to assign x to the value to the class that have the highest value of all. So we compare the values yk of x to yj of x, and then we place x to the class that have that has the highest value for any j. Okay, but the problem is how we identify this yk and yk0, because there are some issues. And to identify the decision boundaries, so the vectors of weights and biases, all we have to do is to use these equations. So what's happening? For example, we have three different regions here. On the border, so a point from here should have equal values for both Ri and Rk. Okay, a point from here should have equal values for Rk and Rj, and so on. So basically, to identify these decision boundaries, so the red lines from this figure, all we have to do is to use this information that on the border the values should be equal for these classes. And from this, if we subtract one from the other, we'll obtain this equation yk minus yj transpose multiplied by x plus the difference between the biases wk0 minus wj0 should be equal to 0. And fortunately, if we use this tactic, we have the guarantee that the decision regions are consistent and convex if y is linear. So if the output is linear, then by using this technique, we will obtain a classification that is consistent and convex. What means that it convex? Well, suppose that we have the point xa and xb, like in the figure, that are placed in region RK. This means that for both xa and xb, we have yk of xa is greater than any yj of xa. So the evaluation for the class ck for point xa is greater than the evaluation for any other classes. And the same is happening to yk, to xb. Now, if we have this situation, it means that for any point in between x hat, that will be an interpolation of the 2 points, so alpha xa plus 1 minus alpha xb, where alpha is between 0 and 1, will have the same property that yk of x hat will be greater than any yj of x hat. So the evaluation for class K for this new point x hat will be greater than for any other classes. So it means that we can use interpolation for points to establish their class. Once we know a couple of points from a region, if we're interested in a new point, all we have to do is saying, okay, I have these points. This point is placed between this point and this point, and that means that will be part of class K. Okay? Okay. Now, how we identify W? In here we have an example with least squares for classification. This is not the right thing to do. It doesn't work well in practice, but it's easy because you've learned it already in least square regression last time with Traian, and therefore you should already know how to do regression, so you can solve for the optimal weights using matrix algebra. Again, if we don't remember what happened there, see the previous lecture, lecture 3, that was presented by Traian, and you'll remember. So basically, what's happening for each class, we have yk of x equals to wk transposed x plus wk0. You use the notation like this, where w transposed is a matrix and x tilde is a vector. Each column of the matrix will consist of the bias for that class, wk0 plus the vector of the weights for the class, and x tilde is simply a unit placed for this bias, and then the value of x transposed. And now what we have to do is to assign the value x to the class that will give you yk, that is wk transposed tilde multiplied by x tilde, the largest value. And to determine w, what you'll have to do is to minimize the error, sum of square error in the case of regression. And therefore, if we have a training set xn and tn, the expectation of the error based on depending on the weights is half the trace of this is the prediction because it's x multiplied by the w, and this is the real target. And basically what it says is the trace of prediction minus target to the POW2. Now, to get the optimal W, what we have to do is to derivate this and to set it to 0. And if you do the computation, then you obtain this formula that is the pseudo inverse of X, of the training matrix, multiplied by T. This matrix is also called Moore-Penrose. Once we have the values of W transposed, we can compute y of x for any new point as being W transposed, W tilde transposed multiplied by x transposed. And this translates to T transposed multiplied by pseudo inverse transposed multiplied by x tilde. And once we have the value of y of x, we know the class of this new point. However, this method doesn't work well in practice, and I'll give you two reasons. First of all is let's suppose that we have the data set from the left, and if the data set is linearly separable, then we will have the magenta classifier is least squares regression. The other one, the green one, is logistic regression that we'll be talking in a couple of minutes. And we can see that both of them are correct. However, if some outliers are also present, then the least square regression will try to somehow explain these points, because least square regression, if you remember from last time, was used when you had a Gaussian distribution, and therefore the least square regression tries to fit the Gaussian on the data set, on the new data set, and therefore it modifies the distribution of the points, and also it modifies the position of the regressor, which is not correct, because even if it would have kept the same regressor from here, everything would have been correct. But only the apparition, the appearance of these outliers confused the regressor and made it do some errors. So one of the problem is lack of robustness to outliers. Another problem is again from the implicit distribution that squared errors imply, which is Gaussian. And this is how least square regression would do in a data set that is not Gaussian. So what we have in here is a data set that have a Bernoulli distribution. We have 3 different classes that are not Gaussian distributed. Logistic regression will work fine. It will establish, for example, the first classifier between the red area and the other areas, and then we'll establish the second classifier to separate the green from the blue areas. However, least square errors, you see that they are trying to fit some Gaussian here, and the results are not very good. So again, least squares correspond to maximum likelihood if the distribution is Gaussian. However, if the targets have different distribution, then least squares doesn't work very well. And since I presented you a method that doesn't work, let's see another method that works, and it's called Fisher linear discriminant for 2 classes. It starts from the idea that a simple linear discriminant function should be or could be a projection of the data down to 1 dimension. However, this projection involves some loss of information, and therefore it tries to identify the 1 dimension to project on, so that to lose the fewest information, and to give the best separation of the classes. And by best separation, we imply minimum loss. And now, how we can find this one dimension on which we should project our dataset? An obvious direction to choose is the direction of joining the means of the two classes. So we have two datasets. We identify the mean of each such datasets. We take the vector that connects these two means. We identify the middle of this vector, and that should be the separator between the class. And the projection should be made on an axis that is parallel to this vector joining the means of the classes. However, there is a problem. If the main direction of variance in each class is not orthogonal to this line, then we will not have a good separation. And we'll see soon what's happening. And based on this observation, Fisher's method says, okay, then if a good option for our 1D that we have to project our data is the vector joining the class means, then we'll consider this, but we'll also consider something else. So Fisher's method chooses the direction that maximizes the ratio of between class variance to within class variance. So we consider the differences between the classes, but we also consider when we decide what is the axis that we'll project on, we also consider what's happening within class, within each class. So we also consider the variance within each of the classes that we're interested in. In this case, only two classes, but we'll see that its generalization involves any number of classes. So basically, this is the direction in which the projected points contain the most information about class membership, again under Gaussian assumptions. And let's see what's happening. So in the left figure, we have the data set. We have some blue points and some red points. And what we see, we compute the mean for both classes. So we have this and this. We join the mean with the line, and the data set is projected on this line. Okay, so this line is parallel to the line joining the mean. And if we take the middle of this vector, of this segment, then this is where we should make the discrimination. Okay, so we set here the limit between the classes. What's in the left should be blue, what's in the right should be red. But as you can see, there are some areas that are not well separated, so we have errors there. And then Fisher says, okay, we'll consider this this line connecting the mean, and this line should be about that, but we'll also consider the direction of variation within each class. So we'll have the maximum variation is on this direction in both classes. Again, in this figure, we showed a simplified example where the two classes come from the same covariance matrix, and therefore they have the same axis of covariation of variation within class. And once we have this, we join them, we take the perpendicular on them, and then we intersect it with the line joining the means, and this point will give me the separator between the classes, and by constructing this perpendicular, this is the direction on which the data set should be projected, because in this direction we will have the maximum information about the within class variation, because you can see that if we project this, then we will have something like this. Okay, and the same situation is happening for the red dots. Is it clear? Because from now on we'll take on we'll go on with the math behind this this visual interpretation. Okay, so what linear transformation is best for our discrimination? We consider this y equal to w transpose multiplied by x, and we'll have to identify this w. First of all, it seems sensible to directly depend this w on the direction uniting the means. So it's m2 minus depends directly on this direction, where m1 and m2 are simply the mean of the points from each class, C1 respectively C2. But also we need to consider small variance within each class. The variance from each class will be summation over all the points from one class from the point minus the mean. So how far these points are from the mean of the class, POW2. And once we have the variations from both classes, we can compute the Fisher's objective function, that is j of w is m2 minus m1 squared divided by s1 squared plus s2 squared. So is the ratio between class variance and within class variance. And we have to go as high as possible with this value. And in this process, we'll change the weights of W, and by changing the weights of W, we'll obtain the optimum line on which we have to project our data. This is what's happening for two classes. If we have multiple classes, then the weights will not be vectors like before, will be a matrix. And now it's a little bit difficult to identify the between class variance, and therefore we'll have to do some math computation. So first of all, we'll say, okay, within class variance is easy to compute, and we'll call it SW because it's the summation of the within class variance for all the classes. And again, it's the difference between the point and the mean of each class to the square, where the means are defined by the 1 over nk, the number of points from each class, summation of the points from that class, and therefore sk will be the point minus the mean to the square. Now, the total variation of the data set will be the difference between that point and the mean of the total data set. Okay, so if we want to compute the variance within one class, we'll have to compute the mean of the class, and then to sum all the differences between the points from that class minus the mean of that class. If we want to identify the covariance, the total covariance of the data set, we'll have to do this summation over all the points and to compute the mean of the whole data set, and then to compute the difference between the point and the mean and square it. Now, the value of m is computed simply like 1 over n summation of xn, which can be derived as nk multiplied by nk. So we take we switch from a summation in number of points to a summation in number of clusters of classes, and we have this formula. And now we know that the total variation is the summation between the between class variation and within class variation, and therefore SB, the variance within class between class variance, is the difference between total variance and within class variance. And this is if we have the formula for total variance here and within class variance here, it means that between class variance will have this formula. Summation over all classes, number of points from each class of each class minus the mean of the whole data set. And now we have the value as B, we have the value as W. All we have to do in order to identify the discriminants is to evaluate SB over SW and to take this to and this process the matrix will be set, and once this matrix is set, we can make the projections on these weights, and we're all set. Any questions? Okay, if you don't have any questions, we'll another discriminant model that you probably know much better, the perceptron. The perceptron describes a whole family of learning machines, but the standard consists of a layer of fixed nonlinear basis functions. We'll be talking about basis functions towards the end of this lecture. And transform the input vector into a feature vector phi of x, and then what we'll have to do is to use a simple linear discrimination function, which is called the activation function, in order to establish if we have a positive or a negative sample. So what we have to do is first use the basis function to transform the point x to some new values phi of x, then we multiply it with the weights, and then we use the step function that will compare the value that is obtained here, so this product, with 0. And if it's greater than 0, then we have the value 1. If it's lower than 0, then we have plus minus 1. These perceptrons were introduced in 1950. They had an online learning procedure. They were considered to solve all the problems of AI. And because of these claims, some symbolic researchers tried to stop this enthusiasm about perceptrons and emphasize their limitation. And due to this fact, and to the fact that the researchers from symbolic AI were much more famous at that moment, the research in somehow stagnated for a couple of years, like 30 years or so. SVMs that we also be talking in one of the future lectures are not any more than perceptrons, but they have a clever way of choosing the non-adaptive non-linear basis functions. So these basis functions phi, and also a better learning procedure than the one that the regular neural nets have. And that would be gradient descent, and we'll see in a moment. However, since SVMs are simply perceptrons, or let's say smarter perceptrons, they have the same limitation as perceptrons in terms of what kind of functions they can learn. And now, if we have a perceptron, the problem is how can we determine W? And like any problem of optimization of determining W, all we have to do is to minimize some error function. But the problem here is that we don't exactly know how to establish this error function, how to define it. So usually what we do, we write down an error function, and then we demonstrate that each step of the learning procedure reduces the error. So basically what's happening to the perceptron, we cannot use a squared error because, you know, the size of the updates doesn't depend on the size of the mistake. So we cannot use squared error. So a different error function should be chosen, and one possibility is the total number of misclassified patterns. That would translate, because the total number is not a good way of evaluating, because maybe we have these, and maybe we have huge errors, but they will count as the same number of misclassified patterns, so it's not a good metric. So instead of finding the total number of misclassified patterns, we will compute the sum of distances on the wrong side of the decision surfaces, because that would be the error, and in this way we'll know how far from the right position are these points. However, again, this is also a bad function because it depends on the position of the decision surface. However, this position, since we have an online way of updating the weights, it means that after seeing each point, the position of W will change. This raises some discontinuities in evaluating the points, and therefore it's possible that after some updates, the decision boundary to move across some data points and make some correctly evaluated points from the previous step to become wrongfully classified, and so on. So this is again another bad, let's say, error function. And finally, the function that is used and is called the perceptron criterion comes from the idea, okay, let's suppose that we have W, so that we know that all the points from class C1 will have the value W transpose multiplied by phi of xn greater than 0, while all the patterns from C2 will have this product smaller than 0. Then the target for the first sample should be 1, while the target for the second case should be -1. So if you make the product of the target with the point, with the evaluation of each point, it means that this is positive, and multiplied by something that is equal to 1 should remain positive. This is negative, and if we multiply this with -1, again should be positive. So if all the points are correctly classified, then what we should have is this formula. W transposed multiplied by phi of xn multiplied by the target should be greater than 0. So if we have errors, it means that this value will be smaller than 0, because either we have a positive point that has the target -1, or we have a negative point that has the target 1. So therefore the error is negative, and this is why we consider it with this minus in front. Minus W transposed multiplied by phi of xn multiplied by Tn. And therefore the error of the perceptron is minus summation of W transposed phi of xn Tn, with all the points that are misclassified. Based on gradient descent, it means that the rule of updating the weights is W at the step tau plus 1 is the W at the step tau minus eta of the gradient of this error with respect to W. So if we derivate this with respect to W, it means that this will disappear and will remain this only this product, phi of xn tn. So basically, what the rule says that is that the weights at the next step are the weights for this step plus, because we have a minus here and another minus here, so we transform in plus eta multiplied by phi of xn multiplied by tn. And this is the gradient descent algorithm. Basically, add an extra component with value 1 to each vector in order to eliminate the bias, because the bias weight on this component is minus the threshold, and since we have this value of 1, when we compute them, we can get rid of that. And then we pick training cases using any policy that ensures that every training case will keep getting picked. If the output is correct, then nothing is happening. If the output is -1 but should be 1, then we will add the feature current weight vector. If the output is 1 but should be -1, all we have to do is subtract the feature vector from the current weight vector. And this method is guaranteed to find a set of weights that gets the right answer on the whole training set, if any such set exists. And also, there is no need to choose a learning rate, and therefore it's kept to 1 because multiplication of W with a constant doesn't modify the perceptron function. It only modifies how fast it reaches the final, how many steps are required to reach the final set of weights. Any questions before we continue? Okay. This is an example. First, we have the initial classification. The arrow is orthogonal on the decision surface and points towards the red points. So what we have to do is to pick this point. We see that is on the wrong side of the classifier. We take the feature vector and we add it to the weights vector, and therefore we obtain this resultant. I'm not sure. Sorry. Okay. Let's see if I can draw this correctly. Okay, so this is the new set of weights that is shown in here. This is how we obtained it. And now we take the next, and we see that again is not correctly classified, and we take the feature vector and add it to the weights vector, and now we have a new resultant. That is this one represented in here, and now all the points are correctly classified. Again, I told you that perceptrons cannot. There are some claims that they can do a lot of things. But there are some simple tasks that cannot be solved by perceptrons. One such task is the implementation of XOR, where we have value 1 if both elements are the same, and 0 if are different, and there is no classifier that could be used to classify this data. Now, we'll continue. So up to now, we talked about discriminant functions. And I told you that the normal continuation would be with discriminant models. However, we'll jump to generative models, and then we'll come back to discriminant models, because I would like, when we talk about discriminant models, to talk also about some basis functions, and first to finish with the models that don't involve any kernels and basis functions and stuff. So we'll continue with generative models, and we'll start with two classes. So we'll have to use a separate generative model of the input vectors for each class, and then see which model makes the test input vector most probable. Now, if we have only two probabilities, we'll use Bayes rules and product rule, and well, we'll have this P of C1 given X equals to P of X given C1 multiplied by P of C1 divided by P of X. Now, if we have two classes, P of X equals to, according to the second rule, is sum over classes. So we have only two classes, so it will be P of X given C1 multiplied by P of C1 plus P of X given C2 multiplied by P of C2. And this is how we got to this formula. From here, all we have to do is to divide by P of C1 multiplied by P of X given C1. So if we divide by this term, it means that it will get 1 over 1 plus P of C0 or C2, whatever, multiplied by P of X given C0 divided by P of C1 multiplied by P of X given C1. Now, this fraction we will be writing, so this is the function sigmoid that is defined like this. And in order to have this sigmoid, it means that this term from here will have to be written as e to the power minus a. And now we'll have to derive this minus a to see what's happening there. So since we have a minus in front, it means that we'll have to revert the so I'll consider only this term, okay, from now on. This term equals to e to the logarithm, and we'll have P of C0 multiplied by P of X given C0 divided by P of C1 multiplied by P of X given C1. But since we have this minus, it means that we will have to revert it, minus logarithm of P of C1 multiplied by P of X given C1 divided by P of C0 multiplied by P of X given C0. Now, another thing that it's important, P of C1 multiplied by P of X given C1 is P of C1 given X divided by P of X. Do you agree with that? So if we divide the terms from here by P of X, it means that we will obtain e to the minus logarithm, and we will have P of C1 given X divided by P of C0 given X. But since we have only two classes, this is equal to logarithm of P of C1 given X, and P of C0 given X is nothing else than 1 minus P of C1 given X. Because you know the two classes should sum up to 1. So we can write this second class as being 1 minus the probability of the first class. Is it clear? So all that I did was to write this P of C1 multiplied by P of X given C1 as being P of C1 given X divided by P of X. So I divided both up terms and down term by P of X, and therefore we obtained this C1 on top at the denominator and P of C0 given X at then denominator, and then all we had to do more was to define the P of C0 given X as being 1 minus P of C1 given X. And using this math, we obtained the value of A as being logarithm of P of C1 multiplied by P of X given C1 divided by P of C0 multiplied by P of X given C0, which is logarithm of P of C1 given X divided by 1 minus P of C1 given X. And this value is called the logit function and is given by the log of odds, because you see this is P of C1 given X and this is P of C0 given X, the positive and the negative class. Now, if we have more than two classes, again we use the same rules, and the probability of the class given X will be P of X given CK multiplied by P of CK divided by P of X, that now is defined by the summation over all classes of P of X given Cj multiplied by P of class Cj. Again, we would like to use to reach some exponentials, so we will write this term as being e to the power ak, which means that ak will be logarithm of this divided by the summation of e to the aj. This is called the normalized exponential or softmax function. It's a multi-class generalization of the logistic sigmoid. And it's called softmax because it's a smoothed version of the max function. Now, if we want to compute the values, we'll have to do some math. So first, assume the input vectors for each class are from multivariate Gaussian distribution that have the same covariance matrix. It's extremely important, and we'll see what's happening if they don't have the same covariance matrix. But let's suppose that the vectors from the classes share the same covariance matrix. Covariance matrix that will be defined like this. And if we have this Gaussian distribution, it means that the probability of X from given CK, so what is this saying is the distribution of points in space for the class CK is given by a Gaussian that is defined by this constant, that is a normalizing constant, multiplied by exponential of minus half X minus the mean multiplied by the covariance transposed multiplied by the covariance matrix multiplied by X minus the mean. Now, if we have only two classes, then the posterior is given by logistic we just saw earlier. So we have P of C1 given X is the sigmoid of A that in our case is W transpose X plus W0. We'll see a bit later because we'll come back to this sigmoid when we'll talk about discriminative models. And the mean, and the W that is involved in here is the covariance matrix to the -1. So inverse covariance matrix multiplied by the difference between the mean of the two classes, mu1 minus mu0, mu1, sorry, mu2 minus mu1. Also, the bias W0 is minus half mu1 transpose multiplied by the inverse covariance multiplied by mu1 plus half mu2 transpose multiplied by the inverse covariance matrix multiplied by mu2 plus the logarithm of the two classes C1 over C2. A picture of the two Gaussian models. Let's suppose that we have, again, as you can see to the left, we have the same covariance matrix for both classes. We have here in the same graph the red curve. It's the probability for the negative class. You see that the highest value for the lower value for x, the highest probability, the higher probability, and the blue represents the probability for the positive class, because you can see that as the value increases to 1, the probability of getting points from this class will increase. So as the value of x goes towards 1, the probability that x belongs to the blue class increases. As the value of x goes towards -1, the probability of the target being in red class goes to 1. If we combine these two, because we have the same covariance matrix, it means that the posterior probability P of C1 given x, it will be C1 being the negative class. You can see that we have high values when x is close to -1, and we'll have low values towards 0 when the value of x increases towards 1. Now, if we want to increase the number of classes, so to make generalization for the situation with multiple classes, we will go from the definition of AK, that is WK transposed multiplied by X plus WK0. And again, WK will be the summation, the inverse covariance matrix multiplied by mu K, and WK0, so the bias, will be minus half the product between the mean of the class to the left and right, and in the middle will be the inverse covariance matrix plus logarithm of P of CK. You can see that the bias when there are only two classes is simply the difference between the biases from class 1 and class 2, because it was a term with minus, it was a term with plus, because when you put minus in front it will become plus, and then it's the logarithm. Instead of having only one class here, it's the probability of class C1 divided by the probability of class C2. And this formula are true only when the input vectors have the same or share the same covariance matrix. Because what's happening here is that if the class conditional densities are coming from the same covariance matrix, then the decision surface between them will be linear, as you can see here. You see that the green and the red classes have the same covariance matrix, but the blue dots, the blue data set has a different covariance matrix, and therefore the decision surface becomes quadratic and is much more difficult to identify. So this is why it was extremely important, and the values that were presented earlier stand only when we have the same covariance matrix. If the covariance matrix is not the same, then there are other issues and the computation becomes complex. Now, maximum likelihood solution. We need to solve this. Once we have the form for the class conditional densities, we can determine the values of the parameters using maximum likelihood. And again, we consider the situation when we have a shared covariance matrix. The data set will comprise of x and tn, the point and 0 for class C2. We have P of C1 is pi, the probability of being in class C1. Probability of being in class C2 is 1 minus pi because the two classes should add to the probability of the two classes should add up to 1. And now, if we, the probability, the joint probability of the point and the class is the probability of the class multiplied by the probability of the point given the class. This probability is pi, as we presented earlier. This probability is a Gaussian with the mean mu1 and some covariance matrix. For the second class, we have 1 minus pi, the probability of the class, multiplied by another Gaussian that has the same covariance matrix, but depends on the second mean. And now when we compute the likelihood, we have to write it as like this. We saw in the previous lecture how we go from here to here. So it's the probability is the product of the probability for the first class multiplied by the probability for the second class. Is the first class to the Tn. So if the sample is positive, Tn will be 1 and this term will remain. If the term is negative, then Tn is 0 and the term disappears. And also is the same thing in here, is the second is the probability for the second class. If the second class, if the point is positive, then Tn equals to 0 and it remains the first term. If Tn equals to 1, the second term disappears. But if the point is in the negative class, then Tn will be 0. So the first term disappears and remain only the first term. Now, to maximize the log of this, first we'll have to compute the log, and I'll erase some stuff from here because I'll need space to write the logarithm of this, and then we'll have to derive it with respect to w to mu1, mu2, and sigma in order to identify the values. So first, we have to compute the logarithm of this, and the logarithm of this will be summation because the product transform in summation. So let's see, summation, and what we will have? We will have Tn multiplied by, being the power goes in front of the logarithm. So we have Tn logarithm of pi plus logarithm of the Gaussian depending on mu1. I will write only mu1 because of the space, but of course it's the Gaussian of xn depending on mu1 and the covariance matrix, plus 1 minus Tn logarithm of 1 minus pi plus 1 minus Tn logarithm of the Gaussian depending on mu2. And now, first we need to identify the value of pi. So what we need to do here is to derivate the terms that depend on. So we need to derivate log likelihood and set the derivative with respect to pi to 0. And now, if we consider these terms, when we consider the terms with pi, it means that we are interested in this term and in this term, because this term doesn't have pi in it, and also this term doesn't have pi. So we will have only summation. So this translates to this one. It's only summation of Tn logarithm of Pn. So Tn logarithm of pi, the first term, plus 1 minus Tn logarithm of 1 minus pi, this term. Okay. Now we have to derivate and set it to 0. So that would be Tn over pi, because the logarithm derivated is 1 over the term. Now plus 1 minus Tn, and the logarithm of u is u derivated, so minus 1 divided by 1 minus pi equal to 0. And from here we have Tn multiplied by 1 minus pi equals to 1 minus Tn multiplied by pi. Do you agree? Because due to this minus, I take the second term to the right of the equal, and I'll have Tn divided by pi is 1 minus Tn divided by 1 minus pi, and then I multiply cross terms, and we get Tn multiplied by 1 minus pi equals 1 minus Tn multiplied by pi, which means that in the end, of course, there is also summation of these terms. So we have also this summation, and we have minus equal to 0. And from here, Tn multiplied by pi, it will disappear both here and here, and it will have Tn minus pi equals to 0. So pi equals to 1 over n, because it's summation, and the summation of pi, it will be n multiplied by pi, equals to summation of Tn. So it means that pi equals to 1 over n summation of Tn. So in other words, is n1 over n, which can be generalized to n1 divided by n1 plus n2. If we have n classes, it will be n1 over the summation of all classes. And this is how we obtain this pi, the probability of the positive class, is the number of points from the first class divided by the total number of points. Now, when we have to find mu1, we'll have to derive all the terms that depend on mu1. And from here, we only have one term, this one, because this is the only term that depends on mu1. The other term depends on mu2, and these terms we already considered as depending on pi. So the only term that we're interested in is this term from here. And when we derive this, you remember that it was an exponential, is logarithm of exponential. So we get rid of exponential and remain only with the term that comes from here, plus some constant that stay there. So we will have this term. When we derive with respect to mu1, we'll obtain that the mu1 is 1 over n summation of Tn xn. The same will happen for mu2. Again, we will have only this term, and as we had for the first term this Tn, now for mu2 we'll have 1 minus Tn, so this is where this term comes from, 1 over n2 summation of the points from that class xn. So the only important information that you will have to remain with is how we compute pi as being the number of points from one class divided by the total number of points, how we compute the means mu1 and mu2 using these two formulas, and then in order to obtain the covariance matrix, the computation is a bit more complex, but what's happening in the end, the covariance matrix is weighted average of the covariance matrices associated with each of the two classes separately. So the covariance matrix will be this formula, n1 over ns1 plus n2 over ns2, where s1 and s2 are the covariance matrices for the two classes. Do you have any question? Now we'll get to the last part, to the probabilistic discriminative models. The advantage over generative models that we just presented is the lower number of parameters that we have to compute in order to determine the right class for the target. And as I told you, this is the reason why we let this class at the end. Up until now, all the classification have been done directly on the input vector x. Of course, with the exception of the perceptrons, where we saw that we have some basis functions. But however, the algorithms are also applicable if we have first nonlinear transformation of x in terms of moving the space from x to a new space that is defined in basis functions phi of x. So why we're doing this? Because by making this nonlinear transformation, we'll get into a new space, we will transform the problem, we will take it into a new space where boundaries between classes are linear in the feature space phi, but corresponding to the nonlinear decision boundaries that are present in the original space X that has the, I don't know, the regular axes OX, OY, OZ, and so on. And to understand better, let's see an example. We have a data set containing red and blue data points. And as you can see in here, the data set are not linearly separable in this initial space. So we have an initial space that has 2 dimensions, x1 and x2. And using these dimensions at x1 and x2, in order to correctly classify the data set, we need a boundary that you can see is circular, is not linear. Okay. So what we are doing is we'll try to change this axis, and we'll go in a different space that has different axes, phi1 and phi2, by using 2 Gaussian basis functions defined in the original space that have the centers in here and in here. So we have one basis function for the blue, one basis function for the red data points. What's happening? If we use these 2 basis functions, then we'll obtain a new space, as in figure from the right, where the data set is linearly separable. There is a mistake here. This value should be 0. and this value should be 1. And I'll show you why. Let's first take a look on the class from one dimension, from the dimension related to the blue points. So the Gaussian denoted by phi1 that is trying to identify the points, the blue points. As you can see, most of the points are clusters here within small distances of the central point. Central point will have distance 0, and therefore, since it has distance 0, it will be placed here. So as you can see, most of the points are relatively close to the center, so we'll have 0 values, and we also have some values from here that are very far away and that are placed at a distance around 1, and these are these points. Okay, so we have these points translated here and these other points translated here. In terms of phi2, the basis function related to the red points, we can see that all the points from the red class are close to the origin. So we can see that they are clustered in here. So all these points from here are placed in here. And we can see that uh, the blue points are placed at a distance that is higher than 0.5. You know, this circle is somehow at the middle of the distance between 0 and 1. So this decision boundary that is not linear in the initial space transforms to this linear decision boundary in the space that is formed by phi1 and phi2. And in this space, you can see that the blue points are placed at the distances that are higher than 0.5, while the red points are placed in this area where the phi2 values are closer to 0. Now, the linear decision boundary is given by a logistic regression model because we have only 2 classes, and we'll talk about this logistic regression. When there are only 2 classes, we can model the conditional probability of the positive class in this way: P of C1 given theta, where given phi, where phi are the basis function, and equals y of phi, meaning is the sigmoid of W transposed multiplied by phi. Again, the sigmoid has this formulation that we will be used when we'll derive the values of the parameters. This model is known as the logistic regression and has the advantage that for an m-dimensional feature space phi, the model has exactly m parameters, so m values for the weights. If we would have fitted a Gaussian model for this data set, we would have had 2 m parameters for the means, because we would have 1 mean for each class, each having m dimensions, and we would also have the covariance matrix having m multiplied by m plus 1 over 2 terms. So it's better to use this model where we have the basis functions that will transform the initial space in a new space that has only m parameters. And we will be using the following data set. So we have phi n and tn. Now, we initially had xn, but since we go in a different space using the basis function, we define phi n as being phi of xn. And this is why the data set that we have is phi n and tn, where tn is either 0 or 1. With this notation, the likelihood of the data is yn to the tn multiplied by 1 minus yn to the power 1 minus tn. And yn is the probability of the class 1 given the basis function phi n. And now to fit the logistic model using maximum likelihood, we need to minimize the negative log probability over the entire training set. And for that, we need to evaluate the error. The error is the logarithm of the log likelihood and is defined like this: minus tn logarithm of yn, 1 minus tn logarithm of 1 minus yn. And we need to identify w that minimize this error. So we need to derivate the error with respect to w and set this derivative to 0. However, the problem is that e doesn't depend directly on w. E depend on y depend on a. You know, y of n equals to sigmoid of an, which is the sigmoid of w multiplied by phi n. So we have a chain of derivatives, and the derivative of e to the with respect to w is in fact the derivative of e with respect to y, because this is what it depends on. And then we have to get from y to w. So first it's the derivative of y with respect to a, because it's a sigmoid of a, and then is the derivative of a with respect to w. And now we have to evaluate this chain of derivatives. And we'll start with this first derivative, which is easier to identify. If we derivate this term with respect to yn, it will come, we have this minus from front, minus tn divided by yn, plus 1 minus tn multiplied by minus 1, because we have minus yn that is derivated in minus 1. With the minus on front, we have this plus, and divided by 1 minus yn. And this is what is in here. When we get to the same denominator, we will obtain yn minus tn divided by yn multiplied by 1 minus yn. Now, we have an as being w transpose multiplied by phi n, so it means that the derivatives of an with respect to wi will be phi I, and the derivative of an with respect to phi I will be wi. So these are easy to compute. However, we also have y as being the sigmoid of an. So it means that the derivative of y to an should be this derivative. Do you know how to derivate it in order to obtain this? Or should I show you? Let's see. So we have 1 over 1 plus e to the minus an derivated. That will be 1 minus 1 divided, sorry. Here is this. So it's a minus in front, and then the denominator is 1 plus e to the minus an squared, and up top we have this term derivated, which is minus e to the minus an. Minus and minus becomes plus, and we'll try to write this one as plus 1 minus 1. Why? Because the first term is eliminating one of the denominator. So I'll continue here. Equals to 1 over 1 plus e to the minus an multiplied by sorry. So it's the first term minus is not multiplied, minus 1 over 1 plus e to the minus an squared. So this one is y, okay? As you can see here, this is y, and it means that this one is y squared. So equals to y minus y squared, which is y multiplied by 1 minus y. And this is the formula from here. And now we have all the derivatives. We have derivative of y with respect to an, derivative of an with respect to wi, and we also have the derivative of error with respect to y. So now we can compute the chain. We have again all the derivatives that we need, and therefore the derivative of an with respect to w will be the product of all this. When you take the product, this and this disappear, and you'll get yn minus tn multiplied by phi n. If we use softmax, the computation will be similar. So we start from this probability where ak is wk transpose multiplied by phi. When we take the derivatives, it will look like this. The error is minus t logarithm of y. And when we take the chain of errors, chain of derivatives, we will get to this formula that is summation of y minus t, so the prediction minus the target multiplied by the basis function. And just to show that softmax is, that logistic is a special case of softmax, we can write the case of two classes with the softmax representation. So it's yi, y1, sorry, it's e to the z1 divided by e to the z1 plus e to the z0. If we divide by this, both the upper and lower terms, we will get to this formulation where this translates to a single term. So we get to the sigmoid. And we see that the logistic is just a special case that avoids using redundant parameters, because adding the same constant to both z1 and z0 has no effect, and the overparameterization of the softmax is used because the probabilities must sum up to 1. Do you have any questions? That was all for today. Sorry for being a bit longer than I should have been, but I hope that by showing you the computation, you will have less troubles in understanding what's behind these models for classification, and that it will be easier for you to understand and to learn for the final exam. If you have any questions, I would be happy to hear them. Otherwise, have a pleasant night, and see you next week. Thank you and goodbye.
Goodbye.
Thank you.
Bye-bye.